Have you ever wondered how ancient Rome, a city of over 1 million people, managed to get fresh, clean water? No, it wasn't magic. It was engineering on a scale that is still breathtaking today. We're talking about the Roman aqueducts, a network of channels, tunnels, and bridges that stretched for hundreds of kilometers, bringing life-giving water to the heart of the empire. For centuries, we've studied their ruins, marveled at their construction, and tried to piece together exactly how they worked. But now, we have a new tool, a way to see these ancient marvels not just as ruins, but as they were in their prime. Today, we're using cutting-edge AI to reconstruct the engineering genius of the Roman aqueducts. Let's dive in. Before we get to the AI, let's appreciate the problem the Romans were solving. A massive growing city needs water, not just for drinking, but for public baths, fountains, industries, and sanitation. Relying on the Tiber River just wasn't enough. It was often polluted and couldn't serve the entire city. The solution was to bring water from distant, pristine springs in the hills surrounding Rome. The challenge? Gravity. The water had to flow downhill, all the way from the source to the city, over varied and difficult terrain. This required an almost perfectly calculated, gentle slope. Too steep, and the water would flow too fast, eroding the channels. Too shallow, and the water would stagnate. The ideal gradient was incredibly slight, sometimes dropping only a few centimeters for every 100 meters of length. This is where the genius of Roman engineers truly shines. They were masters of surveying. Using simple tools like the groma for laying out right angles and the chorobates, a long wooden level, they meticulously plotted the course of the aqueducts. They would trace the contours of the land, finding the most efficient path. When they hit a valley, they didn't just go around it. They built those iconic, magnificent arched bridges to carry the water across. And when a mountain stood in their way, they tunneled straight through it, sometimes for kilometers, all while maintaining that crucial, gentle gradient. It's mind-boggling to think they achieved this level of precision without lasers, GPS, or any modern technology. It was pure skill, mathematics, and an incredible understanding of hydraulics and materials science. The aqueducts themselves were masterpieces of construction. The main channel, or spicus, was typically lined with a special waterproof concrete called opus signinum. This was a mixture of lime mortar and crushed terracotta, which created a durable, impermeable surface. To protect the water from contamination and evaporation, most of the aqueduct's length was actually underground in covered trenches or tunnels. The famous arched bridges we see today, like the Pont du Gard in France, were actually the exception, used only when necessary to cross valleys. They were expensive and complex to build, but they have become the enduring symbol of Roman hydraulic power. They were built to last, using stone blocks fitted together without mortar, relying on the precision of their cut and the sheer force of gravity to hold them together for millennia. So, how did they supply a whole city? Once the water reached the outskirts of Rome, it didn't just flow randomly into the streets. It was directed into a large distribution tank called a castellum aquae. From this central point, a complex system of lead pipes, known as fistulae, branched out to deliver water to different parts of the city. There was a hierarchy to the distribution. Public fountains and basins received a continuous supply, ensuring everyone had access to free, clean water. Wealthy citizens could pay a fee to have a private line connected directly to their homes, a true status symbol. And a significant amount of water was channeled to the massive public baths, the thermae, which were central hubs of Roman social life. This system wasn't just functional. It was a statement of power and civic pride. Now, this is where it gets really exciting. We've studied the ruins, read the ancient texts from engineers like Vitruvius, but it's still hard to visualize the sheer scale and complexity of this system in operation. This is where AI comes in. Using a combination of archaeological data, historical records, LiDAR scans of the surviving structures, and topographical maps, we can now create incredibly detailed 3D digital models of the aqueducts. These aren't just static images. We're using AI-powered simulation software to bring them to life. We can now visualize the water flowing through the channels, see how the system responded to different flow rates, and even test what-if scenarios. What if there was a blockage? How would the engineers have rerouted the water? Our AI reconstruction of the Aqua Claudia, one of Rome's most famous aqueducts, reveals incredible details. We can virtually fly along its 69-kilometer path, starting from the springs in the Subiaco Hills. The model shows us how the channel dips underground, emerging to cross a valley on a series of arches, before plunging back into a tunnel. We can see the precise engineering of the curves and the subtle changes in gradient. The simulation even models the water flow itself. We can see the steady, calm current moving through the spicus, just as the Roman engineers intended. We can peel back the layers of the structure, revealing the opus signum lining and the stone masonry, seeing how it was all put together. It's like having a time-traveling drone, giving us an unprecedented view of this ancient wonder. But the AI does more than just create pretty pictures. It helps us answer real archaeological questions. For example, by simulating water flow and sediment deposition, we can better understand the maintenance challenges the Romans faced. The water from the springs wasn't perfectly pure. It carried minerals and sediment that would build up over time, forming deposits called sinter. This would slowly constrict the channel and reduce the water flow. Our models show how quickly these deposits could form and highlight the constant need for maintenance. Access shafts were built every 30 meters or so, allowing workers to enter the aqueducts to clean out the sinter and make repairs. The AI helps us appreciate that these weren't just build-and-forget projects. They required a dedicated, organized workforce to keep them running for centuries. These AI visualizations also help us understand the final distribution within the city in a new light. By modeling the Castellum Aquae and the network of lead pipes, we can simulate how water pressure was managed and how different districts were supplied. We can see how the overflow from fountains was used to flush the city's sewers, like the famous Cloaca Maxima, creating an integrated urban water system that was centuries ahead of its time. The AI can even help us estimate the total volume of water delivered daily, which was truly staggering, rivaling the supply of many modern cities. It paints a picture of Rome not as a dusty, ancient ruin, but as a vibrant, living city with flowing fountains, luxurious baths, and a level of public hygiene that wouldn't be seen again in Europe for over 1,000 years. The legacy of the Roman aqueducts is immense. They were not just feats of engineering. They were the lifeline of Roman civilization, enabling the growth of cities and supporting a quality of life that was unparalleled in the ancient world. They demonstrated a mastery of planning, surveying, and construction on an epic scale. And today, by combining the old with the new, archaeology with artificial intelligence, we are gaining a deeper, more dynamic understanding of their genius. These digital reconstructions allow us to walk in the footsteps of the Roman engineers, to see the world through their eyes, and to appreciate their incredible achievements in a way that has never been possible before. It reminds us that even with all our modern technology, we can still learn so much from the past. Thank you so much for joining me on this journey back in time. It's amazing what we can uncover when we blend history with technology. If you enjoyed this look at Roman engineering, make sure to like this video and subscribe to the channel for more deep dives into the wonders of the ancient world. Let me know in the comments what ancient technology you'd like to see us reconstruct next. Thanks for watching, and we'll see you in the next one. In the heart of Rome stands the Trevi Fountain, a stunning masterpiece of Baroque art. But the water that flows from it follows a path carved out nearly 2 millennia ago. This is the Aqua Virgo, one of the ancient Roman aqueducts still in operation today, a testament to an empire that mastered the art of moving water. For 1,000 years, Rome was the largest, most advanced city on earth. At its peak, over 1 million people called it home. And this metropolis thrived for one simple reason: its unparalleled access to fresh water. While other cities relied on rivers or wells, Rome had a constant, abundant supply delivered by a network of 11 major aqueducts stretching over 500 kilometers. This was the lifeblood of the empire. So, how did they do it? How did ancient engineers, without modern technology, build these monumental structures that have stood the test of time? Let's travel back to see how a Roman aqueduct was born. It all started at the source, a natural spring high in the hills, sometimes more than 90 kilometers away from the city. The first challenge was surveying. Roman engineers, known as liberators, used simple but ingenious tools. The chorobates, a long wooden plank with a water level, helped them maintain a precise gradient. The groma, allowed them to lay out straight lines and right angles. And the dioptra, a more advanced device, could measure angles with remarkable accuracy. The goal was to create a gentle, continuous slope. Too steep, and the water would erode the channel. Too flat, and it wouldn't flow at all. The ideal gradient was minuscule, a drop of just 1 to 3 meters for every kilometer. Maintaining this over vast distances across varied terrain was a masterclass in precision engineering. Once the path was mapped, construction began. This was a massive undertaking, often involving legions of soldiers and thousands of slaves. Wherever possible, the aqueduct was built underground. Workers would dig a trench, line it with waterproof cement, and cover it with stone slabs. These underground channels were cheaper, protected the water from contamination, and were less vulnerable to attack. They built vertical shafts every 30 to 60 meters, which provided ventilation and access for maintenance. But what about valleys and rivers? This is where Roman ingenuity truly shines. When a small valley stood in the way, they built arcades, the iconic, multi-tiered arches we associate with aqueducts. These weren't just for show. They were a structurally efficient way to maintain the crucial gradient across uneven ground. The Pont du Gard in France is a breathtaking example, a combined aqueduct and bridge soaring 49 meters high. For very deep or wide valleys, arcades were impractical. So they employed an incredible technique, the inverted siphon. Instead of building a massive bridge, they would run the water down the valley slope through sealed high-pressure lead or stone pipes, across the bottom, and back up the other side. Due to the principle that water seeks its own level, the water would rise on the far side, though to a slightly lower elevation due to friction. It was a brilliant, cost-effective solution. Tunneling through mountains was another challenge they met head-on. Using fire and water to crack the rock and sheer manpower to chisel it away, they carved tunnels several kilometers long. The Claudius Tunnel, for example, stretched over 5.5 kilometers. After a journey that could take up to 24 hours, the water finally arrived at the gates of Rome. It flowed into a castellum aquae, a large distribution tank. From here, a complex system of lead pipes, called fistulae, channeled the water throughout the city. The supply was cleverly prioritized. Public fountains, the primary source for the poor, received water first. Then came the public baths, the heart of Roman social life. Finally, if there was any surplus, wealthy citizens who paid a special tax could have a private connection to their homes. This system provided Rome with over 1 million cubic meters of water every day. That's more water per person than many modern cities have today. It fueled the grand baths, ornamental fountains, and public latrines. It powered mills and industries. It was, without a doubt, the secret to Rome's success and splendor. But empires fall. As the Western Roman Empire crumbled in the 5th century AD, its magnificent infrastructure fell with it. Invading armies cut the aqueducts to lay siege to Rome. Without a central authority to manage and repair them, the channels clogged, the arches crumbled, and the flow of water slowed to a trickle. Rome's population plummeted from over 1 million to just 30,000. The great city shrank, its people forced to rely once again on the polluted Tiber River. The age of water was over. For centuries, the aqueducts lay in ruins, silent skeletons on the landscape, but their story wasn't finished. During the Renaissance, popes and engineers began to study and repair the ancient systems. They restored the Aqua Virgo, which became the Aqua Virgin, to feed new fountains, including the magnificent Trevi. Today, we can see the legacy of Roman engineering all over Europe. But what if we could see them as the Romans did? Thanks to digital technology, we can. Archaeologists and 3D artists are now creating stunningly detailed digital reconstructions of the aqueducts and the city they served. Using laser scanning, drone photogrammetry, and historical records, they can piece together these ancient wonders in virtual reality. We can fly over the arcades of the Aqua Claudia, follow the underground path of the Annu Novus, and see the water gushing into the baths of Caracalla. These digital models aren't just beautiful visuals. They are powerful research tools. They help us understand construction techniques, calculate water flow, and experience the scale and complexity of the Roman water system in a way that was never before possible. From the spring in the Alban Hills to the digital realm of the 21st century, The story of the Roman aqueducts is a story of human ambition, ingenuity, and resilience. They are more than just stone and mortar. They are the enduring arteries of an empire, a testament to a civilization that understood the power of water, and a lesson in engineering that continues to inspire us today. Thanks for watching. If you enjoyed this journey back in time, don't forget to like, share, and subscribe for more stories from history. See you next time.